So good morning, everyone. So first, I really want to thank ARSLA, because this is thanks to them that I am capable to present this work today that we perform with my former PhD student, Affiliation, which is which is now graduated. So today I will speak about the involvement of inhibitory neurons in ALS and in FTD, but we are going to mostly focus on ALS actually. ALS associated with FUS mutation. So FUS is an RNA-binding protein that is ubiquitous and multifunctional, that is involved then in a lot of functions, and to do that, it is composed by a lot of different domains, and one of these is the nuclear localization signal that is in the C-terminal part, that is highly conserved in evolution, and that is really important for the regulation of FUS subcellular localization. When this domain is truncated, so this is the case in some familiar ALS situation, it is followed by a truncation that is associated with a very aggressive and juvenile form of ALS. And what is observable is a dislocalization of FUS. So FUS is usually mainly in the nucleus, and when this kind of truncation appears, you have a dislocalization of FUS that is then found in the cytoplasm. But FUS is also found cytoplasmically mislocalized without any mutation. This is the case in some sporadic form of ALS, but also in FTD, and more precisely in FTD with behavioral disorders. And in this situation, so we found again the dislocalization of FUS, but also the formation of some granular stress. So in our laboratory, we generated a different mice model that display constitutive and ubiquitous FUS truncation and a subsequent FUS delocalization in all cell type. When we do that in homozygous mutation, we observed the death of the pups perinatally, indicating that FUS is highly involved in the embryonic step. So we then decided to make the mutation in a heterozygous statement to perform behavioral characterization. And doing that, we observed that these mice suffer from a mildly progressive motor alteration, some feature characteristic of FTD, but I'm not going to focus on that today, or not during this topic at least, and also alteration in cortical inhibitory neurons. So the involvement of inhibitory neurons in ALS is not new. This is something that is already a little bit characterized. And we know, for example, that inhibitory neurons are really important to regulate the activity of upper motor neurons that are localized into the cortex, and also some inhibitory neurons in the spinal cord, to modulate the activity of lower motor neurons. What is known is that in ALS-FTD spectrum, there are some inhibitory neurons alteration, not necessarily a degeneration of these inhibitory neurons, but an alteration of their functions that leads finally to hyperexcitability of motor neurons, so either upper and lower motor neurons, that could lead to the degeneration of these neurons. So, we were there at the onset of the Felicity thesis, and we decided to study more precisely the role of inhibitory neurons in ALS associated to FUS by creating two new mice models using the Krelox recombination technologies and the LOXP system. And doing that, we were capable to either induce the mutation of FUS in all the cell types except the inhibitory neurons or to induce the FUS mislocalization in only and solely in inhibitory neurons. And today I'm going to speak only about these results. So we crossed VGAT mice that allow the expression of chlorocombinase only in inhibitory neurons. I mean, in neurons expressing VGAT promoters, so mainly inhibitory neurons, with the mice that we called cuttable FUS, in which you have two log space sequences that surrounded the NLS domain. And by doing this crossing, this allows us to have either heterozygous or homozygous mice in which we have either a partial mislocalization of FUS or a complete mislocalization of FUS only in inhibitory neurons. So our first surprise was actually to observe that in our homozygote pups, so they're in red there, so you have the homozygous in red, the heterozygous in orange, and the control mice in black. And this is a representation of a survival curve, actually, so the percentage of survival depending on the age. And we were really and deeply surprised to observe that almost half of our pups, as you can see there, of our homozygote pups actually died around P20. And it was interesting for us because this is exactly during the same time windows that occur a physiological phenomena of synaptic pruning leading to the inversion in the proportion of excitatory. Come on, I lost my pointer. Okay, of either I'm going to do. Sorry. Of either excitatory neurons or inhibitory neurons. So we decided to focus the next step of our study either on pups at 5 days or 15 days of age. So first we look at the body development, so taking the body weight and measuring the body weight and the body length. And what you can see there is that at P5, there is absolutely no difference between our different genotype. So there, no alteration. But the story was really not the same when we focus at P15. As you can see there, we already obtained a very important and significant decrease of both body weight and body length in our homozygous mice only. So we decided to look a little bit more, to focus a little bit more on motor performances. So as you can imagine, at P5, motor assessment is not really easy to do. So we decided to make different tests, and I just show you this one today, but none of them actually show any differences. So this is the surface writing test, and this involved both motor reflex and trunk control. And as you can see, no motor alteration at P5. The time to writing is the same, whatever the genotype. So we need to change a little bit this assessment because at P15, this test was really too easy for all the mice. So we decided to, let's say, make an equivalent that is more suitable. That is the negative geotaxis test. So the idea is to put a mice in an inclinated plane, the head down, and to look the time necessary to go back in the right direction. And and it involved both motor and sensory reflex, and also motor coordination, and let's say a good vestibular inputs. There, no alteration were observable. We decided then to look at the four-limb hang test, so also known as the inverted wheel test, and I think this representation is quite self-evident, and it's allowed to assess both arm and paw strength. And there, what you can see is that whatever we look, if we look the hanging time or the holding impulse, so this one is just a multiplication by the weight, we have alteration that start to be observable there in our homozygote mice again. So it's looked like we have a progressive motor alteration development. So we wondered there if this alteration was associated with the loss of lower motor neurons. So we decided to make some immunostaining of the motor neurons in the ventral part of a lumbar spinal cord section. So from there, I only focus on homozygous mice because heterozygous and control mice show the same thing. So we decided to focus more precisely on homozygous there. And as you can guess, we didn't have any difference in the number of lower motor neurons in our spinal cord section. So it looked like there is actually no motor neuron degeneration. So we performed this test at P15, as at P5, nothing pops up. So next question is first properly localized. So to do that, we decided to assess the ratio between the signal obtained in the cytoplasm and the signal obtained in the nucleus after making a staining of FUS protein. And as you can see there, this ratio is more or less the same, so indicating that FUS is found mainly in the nucleus, in control mice and in truncated mice. So next question, what about the neuromuscular junctions? So there we use some tibialis muscle and decided to make two labels actually neuromuscular junctions to look if the rate of innervated junctions is the same or not. And there we obtain, again, no difference between our control mice and truncated mice. So we finally go and look at the upper motor neurons. So we look in the cortex, actually. And so you have there the DAPI that's allowed just to label the nucleus. You have there the first staining to actually look at the potential mislocalization. The neoN staining that's allowed to label all the neurons, actually. And the parvalbumin staining that's allowed to label specifically inhibitory neurons, part of inhibitory neurons. And we found it did, as you can observe there, an important mislocalization of FUS in the cytoplasm of our homozygous mice. So we have this localization, and it looked like our motor alteration are mainly associated to cortical alteration rather than spinal alteration. So in this study, we demonstrated that a truncation of FUS-NLS signal in domain in inhibitory neurons specifically induces abnormal death around P20 that is associated with motor alteration but not detectable in the really early stage. That these alterations are not due to a lower motor neuron loss or FUS mislocalization in the lumbar spinal cord motor neurons, and that this is not due either to a neuromuscular junction disconnection. So, of course, we wonder what's wrong. Of course, you can imagine. So first, we were thinking that it might be due to alteration for the eating process. You might know that at P20, so the age at which half of the pups died, this is the weaning onset. So maybe that's our actually perinatal abnormal death was due to problem to start eating solid food. So to answer this question, we actually decided to propose two conditions, so the normal one and one in which the mice have access to facilitated food intake. So we propose a wet food or gel diet food. But doing that, as you can see there in red, it actually didn't change the dramatic loss of weight in our homozygous mice. This is the dashed line there. And it also didn't change the mortality of our pups. So making food more easily consumable did not change the rate mortality of our pups. So it looks like it's not related to chewing problems. We then decided to look at something else because we observed that during our different behavior, it looks like our pups present some transient period of inactivity. and as first have a role in regulation, inhibitory synapses and neural activity level, we wonder whether maybe those mice could present like epileptic-like events, such as absence crisis or those kind of things. So to do that, we started collaboration with Delphine Roussel to make some EEG recording and video recording, but unfortunately, due to a limitation due to the size of the pups, the implant could not be positioned correctly, and we were not able to have a good recording to answer this question. So right now, I still don't know why. I'm sorry, but I still don't know why these pups are dying at this moment. So end of the story for me today. I want to deeply thank Félicie Lerenc for all the work she made during her amazing thesis. I also, of course, want to thank all the people from our my lab. I also deeply thank Delphine Roussel, because even if we didn't have an answer, we anyway try something, so it's important. I also thank Pascal Kessler, who helped me a lot for all the acquisition, image acquisition and so on. And of course, all the zootechnicians for taking care of my mice. I thank you for your attention. And of course, I again deeply thank ARSLA for helping me to do this project. Thank you for your attention.
Il y a des questions?
Thank you very much. I wanted to know if you have a large change in the cellular mislocation of FOS in the inhibitory interneurons in heterozygous versus homozygous, because apparently you have large differences in the behavior.
Actually, it was not as clear as that. It looked like it's a little bit, the dislocalization is a little bit higher in the homozygous than heterozygote, but it's not as tricky as we could expect it.
Yeah, thanks so much for the presentation. I got a technical question. So you have like this VGAT system, CRIS system. Which neurons, inhibitory neurons exactly are you addressing in the path albumin ones in the cortex? Not only.
No. It's more larger.
Mm-hmm.
Actually, this is also targeting the glycinergic nerves. So glycinergic and glycinergic nerves. It's supposed to be larger than just
Okay, I see. So the path albumin neurons you showed were just like a sort of proof of concept that the truncation. Well, thanks. Okay. Regarding the MNJs, which I might have missed it, which muscle did you check for? Sorry? Okay. And probably. Yeah, and easily accessible, right? Yeah. I mean, it might have been the wrong muscle, though. That's just like one thing that it's just like the other different muscle to assess where you could see a denervation, maybe. Thanks.
Actually, we made some perseverance on the other and we didn't see any differences.